Hello again from D&N Custom Creations. My name is Dan. The last video I did was about the initial height sense for the Langmuir's plasma cutting table. And I mentioned that I would do another video on torch height control, so that's what this is going to be. I've had people in the past tell me that my videos would be a lot shorter if I'd talk a little faster, and I'm sorry, I'm a Southern boy and I'm old, so sometimes it's a little hard for me to even think that fast. But I want to tell you what started this whole thing. I'd asked the Langmuir support. I said, look, I want to cut some stuff and stainless, and it looks like the cut height is all the way down, goes from what I'm normally using steel is like 0.06, is down to 0.02. And I knew that torch height control, if I'm cutting at that height, it doesn't take much before that torch could actually contact the work, because you're down already pretty darn close. And I asked them whether or not I should disable torch height control. Well, the response is what kind of led me down this whole process of looking, trying to understand a little better the the initial height sensing and torch height control. Because they basically said that they recommend, and I specifically talked about the hypertherm cut charts, and they said if you look at the hypertherm cut charts, you'll notice that they also provide you a voltage, and that they recommend that you probably ought to use that voltage, go in and set that as your nominal voltage in the torch height control, instead of depending on just using the cut height. So I want to go through that a little bit of discussion on how torch height control works and really what they were trying to get me to try and do. So let me set up a little bit. I'm going to walk you through some charts, and everything I'm going to tell you today came out of Langmuir's torch height control guide. But if you're like me, who reads the guides? But in reality, some good stuff there. And so I'm going to try and walk through that without it being as dry as trying to read the guide. Okay? So here's a little chart showing you what I'm going to attempt to do in this particular video. I'm going to describe the torch height control, how it operates. I'll discuss the Langmuir's, the torch height control when you use smart voltage. Then I'll also talk about how if you use THC using nominal voltage and start smart voltage, what's going on there. And then I'm going to demonstrate the method for determining the nominal voltage. In particular, in my case, it was for sheet thicknesses that I couldn't find in the cut charts, but it also would be something when you're trying to improve the quality of your cuts, etc. So first let's talk about how the Langmuir's torch height control operates. And again, this came out of the guide. So if you don't want to listen to me, just read guide. But for this discussion, we're going to assume that you have a selected torch height control, and actually it's in operation. Obviously, you can turn it off and disable it. But for all of the discussion, we're going to assume you want it. Torch height control is not utilized for the pierce part of a cut loop. The pierce height is, if you looked at the last video on initial height sensing, that's the IHS that sets and utilizes the pierce height. And torch height control is only utilized in the cut phase, and only if certain criteria have been met. It's enabled at the beginning of every cut loop, and it's disabled or reset at the end of every cut loop. If you are a G-code person and you go in and look at the cut loop, H1 enables torch height control, H0 disables it. And again, even though it's enabled, there's still some criteria that have to be met before it actually operates. It's based on the fact that the voltage, your arc voltage, changes as the torch moves away from or closer to your target plate, the plate you're going to cut. And in fact, as the torch gets closer to the plate, the voltage lowers. If it's higher to the plate, it gets higher voltage if the torch is further from the plate. And there's some target height and target voltage that the torch height control is trying to maintain, and that's what moves the torch up and down, trying to maintain that value. There's also torch speed that can affect the voltage. And so, you know, as torch height control attempts to keep you at the desired height, the speed of that torch, actually in the XY motion, not in the Z motion, but in the XY motion, that speed can also affect that arc voltage. And if you get to, say, doing a sharp corner where the speed slows down, or you're cutting a small circle, etc., the arc voltage will increase. Well, the torch height control thinks, oh, the voltage is increasing. Therefore, I've moved away from the plate. I better move downward again and get back to my the voltage I'm looking for. And this can plunge your torch towards that plate. And if you're already using a very small cut height, well, you could actually wind up contacting the plate. Wouldn't be a good thing. So there's two user selectable parameters that are provided to solve that. That's the torch speed cutoff setting and the Z speed factor. Now let's talk about each one of those. First is the torch speed cutoff setting. This is XY speed, it's not the Z speed. So when you select in your post process saying, okay, I'm cutting 11 gauge metal, therefore my best cut speed is, I don't know, let's just say 125 inches per minute. Well, the torch height control knows that and is monitoring the torch speed in your XY direction. So if the live torch speed, you know, as it's watching, if that falls below some percentage that you're going to set in your settings, then the torch height control actually momentarily disables and stops making any Z correction to try and, you know, maintain a voltage level until that speed comes back to within the range that is set. Looking at our example of the torch height control settings, in this area of Z factor, you see it's set for 45%. So if your program speed was, say, 100 inches per minute, then torch height control would actually turn off whenever that live speed falls below 85 inches per minute. And that setting you can set to pretty much anything. That happens to be the default value. All right, the other one is the Z speed factor. Now this is the Z speed, the motion of the torch in the Z axis. And that's used to kind of tune that Z travel speed when torch height control is in control. So the Z motion is set to a percentage of the XY. So if your XY motion is fast, say you're cutting some real thin stuff and you're up to, you know, I don't know, 200 inches per minute, well, then your Z motion is also fast. So it can kind of keep up with that. And this is especially important when you've got a bow in your plate, for instance, and as that's moving. If the XY is moving fast and that plate is bowing, well, then your Z motion better keep up with that. Otherwise, you could wind up crashing into the plate again. So in our example here, we're set our Z factor at 15%. So if in the example, if the XY speed is 200 inches per minute, then the Z speed would be 15% of that, or down to 30 inches per minute. Now you're cutting something and your XY motion is slow because maybe this is thick material. Well, if you drop down to 50 inches per minute, then your Z speed is also going to drop. You'd be down to 7.5 inches per minute. Note that according to the guide, the max Z speed is 60 inches per minute. So if you happen to set this value to something and it wound up driving you to a Z speed factor, a Z speed of over 60 inches per minute, it's only going to go as high as 60. From the torch height control guide, again, you know, if your plate is especially warped, you may need to increase your Z speed factor so that Z axis can keep up. And they give an example here, using a 5% Z speed factor, you can correct up to 4 inches out of flat over a 48-inch distance. So They recommend that you use the default values, and I personally don't have any knowledge of why that wouldn't be a good idea. Let's move on now into the smart voltage. It's enabled when you as a user go into the torch height control settings panel and put a 0 in the nominal voltage and hit save. Nope, there's a duplicate of that. Sorry about that. If smart voltage is enabled, then you will see smart voltage shown in the torch height control panel when you're looking at the fire control panel. Now you will see that displayed as smart voltage when the machine is not cutting, or the machine is cutting, but the criteria to activate torch height control has not been met. So what's the criteria that must be met? Okay, so smart voltage assumes that the cut height you entered in your post-processor is correct for the material being cut. Because when it starts cut at that value that you've selected for cut height, it's going to start measuring the arc voltage. And that becomes the target voltage. So if you selected the wrong height, well, torch height control is not going to fix your problem. It won't correct that wrong choice. So it's important that you start out selecting at least the correct cut height when you use a smart voltage. So torch won't turn on, the torch height control won't actually start manipulating the Z of your torch until the criteria has been met of the offset value has been met and it's been stable. So first of all, if you look at the offset and distance, this for smart voltage, that's the criteria that you have input. These happen to be default values, but that's the values that it starts out with. It says, okay, I'm not going to even attempt to do torch height control until I have traveled at least the offset value, in this particular case, 1/4 inch. Then it comes up to the next, and once it's gone 1/4 inch, it starts sampling the voltage. In fact, when this value here, 50, it says does 50 samples in that next 1/4 inch, and it looks to see if the voltage is stable. If it's stable, then it's happy, and that becomes the nominal voltage. If it's unstable, it won't do that. And I have not been able to create a condition in which it was unstable for that 1/4 inch, so I'm not sure what would happen, but that you must be stable for that 25 thousandths, and then that stable voltage now becomes the target voltage for that cut loop. And the torch height control will move the torch up and down to try and maintain that voltage. Now, again, notice that's for that cut loop. If the next cut loop, it turned out that, these criteria weren't met, well, then it's not going to be active. And so if you have a cut loop that's cutting a small hole, in which you've not traveled a total distance here of at least 1/2 inch, well, torch height control is not going to come on at all. And if you have a condition for whatever reason, the voltage is not stable over that distance, then it's a possibility that it won't be in operation either. All right, so during a cut loop, when the criteria has been met for a smart voltage, then the nominal status button is going to display that target voltage. So you will see, and here you see the little icon says smart. That tells you as an operator, you watching the panel, that smart voltage is being used. And once it meets the criteria, it's gone a 1/4 inch, and then it's gone the next 1/4 inch, established a stable voltage, that stable voltage is going to display, and so that becomes the target voltage that now the torch height control is going to try and match. The live voltage is what it's actually measuring at the instant of time as it's moving. Now the tolerance was set back in the setting of 1.5 volts. And so as long as the live voltage is within 1.5 volts of the target voltage, torch height control is not going to do anything, not going to move at all. If it moves above or below that value, then you're going to see the ups and downs because that torch is beginning to move until it's trying to get back to this target voltage. So in our particular example, if this is the nominal voltage, then if it will only go up or down if that's above or below that value. So if the voltage is greater than 116 volts, it would move down. If it's less than 113 volts, it would move up. And the stoplights here will tell you in real time whether it's actually moving that torch around or whether everything's okay. You're within that 1.5 volt tolerance, will be okay, and that's how you will read those panels. Or let's say you don't want to use smart voltage, you want to use nominal voltage. Well, then you go back into your torch height setting panel and you change your nominal from 0, which tells it you want smart voltage, to whatever nominal voltage that you want to use. Now, the question is, well, what is that? Okay, so the desired arc voltage obtained comes from your cut charts or by performing test cuts to determine the best quality of cut height and recording that arc voltage and using that as the nominal. All right, so let's do the first one where you're using your cut chart. So here's a cut chart from Hypertherm's manual for mild steel, 45 amp air, and using a shielded consumables. And what I wanted to point out is you notice that all the way from a 1/2 inch to 16 gauge, it's the same torch height for cut and the same pierce height. But when you look over here into the voltage settings, they vary. Now they're the same here for these small ones, but then they begin to change slightly as you go up in thickness. Same thing for production settings. I was looking at just the quality settings. Now, again, we talked about at the very beginning, Langmuir support recommends that when you're using torch height control, it's the voltage values that should be used instead of the cut height. Obviously, you've got to have that cut height to know where to start, but then they recommend that use the voltage so that it tries to get to that voltage using the torch height control. So what I'd like to do is I'd like to demonstrate the method that they recommend in the manual for determining that nominal voltage and using that to come up with a nominal voltage. You might need that if the voltage for the sheet thickness isn't in your cut chart. If we go back to this cut chart, you notice that there is no 11, 12, or 13 gauge. Well, I cut a lot of 11 gauge, and there's nothing in here. Now, in the past, have just basically looked at the speed difference, and I've kind of interpolated in between here to come up with a best cut speed. But in reality, I should probably be looking at voltage speeds. Well, it's not there. So what do I do about that? You would also use that if there's no cut chart for a material you want to cut. Let's say you want to cut copper. Well, in my Hypertherm manual, there is no cut chart for copper. So I might need to use this method to try and find out what that is. In addition, if your cut chart voltage isn't giving you the cut quality that you think it should, now again, assuming that all the other pieces are in working order, such as you got a good ground, your consumables are good, you got good clean dry air, we got the right flow, that your starting cut height is accurate, there's no binds in the Z motion, the torch height switch is working like you intended. If all those other things, all these things are right, and you're still not getting the cut quality that you think you should, well then maybe you want to do this method of determining the nominal voltage and using that to see if that won't help correct your problem. Down here when we talk about this cut height is accurate, if you remember from the initial height sensing video, when in the post processor, there isn't a value that's added to whatever you select to try and compensate for spring back and backlash, etc. And so if you say, I want a 20 thousandths cut height, but you've selected something in your post processor, etc., well, that could actually be sitting at 27 or 30 thousandths instead of the 20. So we need to make sure that your cut height, starting at cut height, is accurate if you're getting some quality problems. All right, let's actually talk about this, how you come up with this nominal value. And they do it in the chart, or in the guide. They recommend doing a line test, they call it. And that's basically cutting an 8 to 10 inch line using the straight cut line utility in fire control at the desired cut speed and amperage for a given material, and entering that as a voltage value, as entering this voltage value as the nominal voltage before cutting your part. Well, what do you got to do to actually run that line test and get that nominal voltage? First, and they don't, I'm laying it out in an order. They kind of skip over some things and assume that you've done some things in the guide, so I'm going to try and make it a little more easy for me to understand. First, you got to disable your initial height sensor, because you're going to jog your torch down to the material at the ideal cut height, and if you've got them in the chart, use them. If not, you're going to have to make some assumption based on your, hopefully, knowledge of what you've been cutting. So it's important that because if you don't disable initial height sensing, when you start trying to do this cut, you're going to get an error. So when you're jogging your torch down to a material, here's where you can do an accurate. You use a feeler gauge, you can use some other way of measuring, so that if you're trying to shoot for 20 thousandths torch height, well, then you can use gauges, etc., and make sure that when you jog that down, you're sitting right at 20. It takes out some of these other backlashes and springbacks and some of these other things that happen under initial height sense that might give you a little bit different value than what you're trying to achieve. Next thing is you got to turn off your electronics box and unplug the Z-axis connector from that enclosure. And they don't tell you why, they just tell you to turn it off. In fact, they don't tell you to turn it back on, but you got to in order to run the line test, obviously. But your stepper motor that's driving your Z-axis, when that's powered up, obviously there is current going through that, and it's creating a magnetic field, and that magnetic field is actually one of the parts that allows that stepper motor to operate. Well, if you were to unplug that connector without turning your electronics box off, that magnetic field will instantaneously collapse. And according to Lenz's law, a change in magnetic field will cause a electronic current to flow in the conductor. And the faster it changes, the higher that induced voltage is going to be. Well, if you unplug it, that's pretty much instantaneously. Therefore, you get a high spike that could come back through that connector. And if it just so happens that it hadn't been completely unconnected, you've lost the current that caused the field to collapse, but you're still connected by maybe 1 or 2 pins, that can send a induced voltage, a high voltage, back into the electronics and cause damage. Anyway, so you've turned it off, you unplug the Z-axis connector, you turn it back on, and you run the line test while you're monitoring a live voltage. And hopefully you have done a straight cut using the straight cut command, so you know how to set it up, and you determine the length of cut, which they say use an 8 to 10 inch line, etc. And you're watching this live voltage. And during that 8 to 10, you will see kind of like what that live voltage settles down to. It'll vary a slight amount, but it'll settle down to some number. Well, you take that number now and you go back after you've got that number, when you get ready, then that's what you put in your torch height control settings nominal. You put that number in. That now will no longer use smart voltage, and it'll start operating pretty much instantaneously, but it will be trying to achieve that number. What I wanted to mention is if the cut quality is adequate using that monitored live voltage, great, you're all set, use that. But if the quality is not good, then try a different cut height and play around with those until you find the best quality is determined, and then use that voltage. I will demonstrate that, and we'll see if we can't determine and show how that live voltage is being done. Okay, we're getting set up to demonstrate how to determine the nominal voltage. In my particular case, I'm going to be cutting 11 gauge. That's not in the cut charts. So here's the way I'm set up. You can see I'm doing a straight cut. I've enabled the straight cut program. I'm going to go in the plus Y direction because I want to cut, I don't want to cut cross slats. I want to cut with slats actually where there is no slat. I'm going to go 9 inches. Remember it said go 8 to 10. Okay, well I did 9. My cut speed, I went into the cut charts and I interpolated between 10 gauge and 14 gauge what 11 gauge would be, and the interpolation says it should be 153. I'm going to use a 0 pierce delay because I'm actually going to do an edge start because I want to start at the cutting height that I believe is what it should be. So right now I'm going to use the cut chart cut height that says 60 thousandths of an inch. So I'll generate that program. And notice in here it says doesn't contain any torch height control activation points. Yep, that's true because I don't want any. And now I'm set up to exercise that straight cut. And I'll move you over to that so we can take a look. So here I've jogged the torch down until I'm sitting at the 60 thousandths that I'm shooting for. Now, since I'm doing an edge start, I need to come back away from that. And you can't go too far because once you start running, if the arc doesn't see a cut, in a pretty short amount of time, it will stop. Okay, we're at the right height. We're ready to go. We're going to do 9 inches and see what we got. Okay. We'll let the cooling cycle complete. I'm going to come back here to the starting point. I'm going to come a little farther away. I didn't quite get an edge start. And this time, instead of watching the torch, we're going to watch the live voltage because that's what we're going to watch for because that's what we want to set for a nominal voltage. I'll bring you back. Okay, here we go again. This time we're going to be watching the live voltage and see what values we get. All right, we saw that we were kind of on an average about 126 volts. Okay, before we actually use that 126 volts that we measured, we want to make sure we're happy with the cut quality. So the last one here is the one that we were actually watching the monitor, and I'm real happy with that. Man, there's no dross to speak of. Interestingly enough, I did this first one with the torch height set a little higher than 60 thousandths. I think it was, actually I'm sorry, a little closer than 60 thousandths. And it had some dross. The second one was at 60 thousandths. The third one was at 60 thousandths. So I'm happy with that cut quality. So that's what I would use to set up for doing my cuts. And basically what I do is I'd come over here and I'd go into my settings, and here instead of 0, which uses smart voltage, I would use and hit save. Get out of that panel. And now what you notice in here is, sure enough, there's my target voltage. Now I'm going to hook the Z back up, and I'm going to do another cut with IHS and all the other stuff going on. And let's take a look and see and compare the cut qualities there. Okay, we have entered the 126 volts as our nominal. We're going to be watching the live voltage there to see how well it keeps up with that. Torch height control is turned on. I've also turned on the initial height sensor down here, because if I didn't, we're essentially repeating the test that we did that said, yeah, that's a good height. So I'm going to let the initial height sensor do its thing. And I set a pierce delay now. Since I'm not doing an edge cut, I'm doing a pierce delay because I'm going to pierce it and then cut. So right now it is set for a pierce height, let's see, a cut height of still 9 inches. Cut speed is 153. Okay. I don't know if you are keeping an eye on that live voltage. Let's run it back and do it one more time. I better do it a little faster. All right. So now watch this live voltage and compare. We're trying to get 126. Let's see what we wind up with. All right, it was within the tolerance value, so the torch did not go up or down. For this last cut, I've artificially raised the plate on one end to kind of represent a bow. So I've raised that, there's 2 pieces of 1/8 inch, so that's raised up, about 1/4 of an inch. And we're going to see if, when we start there, we're going to see if the torch moves to adjust for that height change as it goes back to the other position, which is where it was, the other end of that was where it was originally. So when I hit go here, it's going to be starting high. So it's going to start at the 60 thousandths above the plate, but as it moves, it's going to see that plate dropping away because of the incline that I've put in it. And we're going to watch the up and down buttons and see if we see anything happen. Okay, you saw the OK and the down flashing on and off. As it moved, it got beyond that threshold value that I had set, the 1.5 volt, and so it moved it down. And then it went for a little distance, said, oh, I'm past it again, I got to move down again. So you saw the OK and the down flashing on and off, which is telling you the torch height control is moving that torch, trying to keep to that 126 volts. Now we're going to look at the cut quality on that inclined plate. I think what you're going to see is really fascinating. The first thing I want to point out is these first two were done using the initial height sense. And if you remember from the initial height sense video, if you set this to 0.06, because of the backlash and spring back that's inherent in the commands and in the post processor, etc., it usually doesn't wind up at 0.6. It winds up at something a little different. And the dross here is terrible. This third one, it started out just as bad. But right along in here where it says, hey, I'm beyond that 126 volts, I need to correct for that, and it began moving it to try and get back to that 126 volts. Look at the cut quality, how it changed. So once the torch height control took over and tried to get back to that 126 volt value, it made a big difference. Why didn't it here? Well, it was trying to reach that 126 volt value, but it was assuming that the torch started at 60 thousandths, and it wasn't 60 thousandths. That's my explanation. Now, maybe I'm wrong. Now, is that dross hard? Yeah, it's not coming off real easy. But look at the difference once torch height control tried to correct to what I had told it was the best value. Very interesting. So I've uncovered what probably made such a difference in that lousy dross that we had on the first two and portion of that third one once I turned IHS on. I'm looking at the G code here for that cut, and you notice down here there's the pierce height 150 thousandths, but and you know, for there's a delay 0.7 seconds. But look at the next command. Apparently in that straight cut, when it generated this program, it put the cut height at 80 thousandths. Well, we already know when we cut it at 60 thousandths, it made a darn good looking cut. And that's what we used to come up with that 126 volt nominal. When it was set at 80 thousandths now, not only if it was exact, it would be 20 thousandths more than what I intended it to do and where the good cut quality got. But when you remember what we learned in the IHS, there's actually an amount that's added to that. Not added to it, but because of the backlash, that is probably sitting at 90, in my particular case with 13 thousandths backlash, it's probably sitting at about, I don't know, over 90 thousandths cut. That, in my opinion, is why we're getting such lousy dross. If I could edit that, and I don't know where that actually is stored, I could go and edit that and see if it made a difference. Or I could create another cut line with a code that I come up with and set that to a different value and see if that made a difference. But I'm almost 100% confident that it's this value plus the artificial value that we learned from my initial height sensor that wound up with the torch being too high on that cut to get good cut quality. And as the torch moved in that inclined place where it tried to drive it back down to the 126 volt that we intended, and this number now, that might where it started, but it began to drop and drop and drop. It got down to the point where it was making a good cut. Well, I told you at the beginning of this, I was going to talk about torch height control, and I was going to try and speed up my talking a little bit and shorten this thing up. I failed. This thing is still a lot longer than I intended it. But I think we've learned some interesting things here, especially the process of coming up with the nominal voltage and what's going on in the straight line command. I don't know that if it always sets it at 80,000. I need to play around with some parameters there and see if I can find out why it set that cut height at 80 thousandths. I didn't set it there, so I need to understand that a little bit better. All right, I think that's it. Got some questions or comments, please leave them in the comment section. I appreciate you watching this. And this is D&N Custom Creations. Till next time.